Okay, go.
Well, good evening, everybody.
Oh,
My
stand
name
by. It didn't start yet.
oh,
Sorry about that.
okay.
Okay, now.
Good evening, everybody. My name is Burt Dicht. I am Managing Director of Membership for the National Space Society. So welcome to our Space Forum this evening. This is going to be a little different tonight because I'm stepping out of my role as moderator to actually be the presenter. And I wanted to introduce you to two people I've been working with over the last several months. And they are going to be very involved in our organizing and also moderating space forums as we go forward. So first, I would like to introduce Stephanie Erickson. Stephanie is a marketing and communications consultant, of course, an NSS member. Welcome, Stephanie.
Thanks. Happy to be here, Bert.
Great to have you. And I'd also like to introduce Sadia Ahmad. Sadia is also an NSS member and also is a SEDS member, Students for the Exploration and Development of Space. And she is actually going to be doing the introduction tonight. So Sadia, welcome.
Hello, everyone.
Very good. So what I'm going to do now, everybody, is turn this over to Sadia to do the normal things that I typically do when we start a space forum. So Sadia, it's all yours.
Thank you. So, hello, everyone. My name is Sadia, and I will be moderating this session along with Stephanie. Today, we have with us Burt Dicht as our speaker. He's a managing director of membership at NSS, and his presentation is about from Moonwalks to Spaceplanes, the story behind the Space Shuttle program. First, we'll go through our virtual etiquettes, then our NSS announcements, our upcoming space forums and town halls, then program, and then we'll get to the closing. So first, for our virtual etiquettes, as you always know, you have to post your questions at Q&A function of Zoom. Feel free to post your questions in the chat as well. We will love to take your questions as we go along. Be respectful of the panelists and the audience. Now for our announcements, we have our flagship conference coming up in June. That is from June 19th to 22nd. And we are thrilled to invite you to our conference. We have about 20 amazing sessions in the conference. And one of the sessions is about space history, where you will find some great speakers talking about astro restoration. We have one more new session introduced to the conference, that is the Rising Stars. And here you will find our young professionals and the college students talking about their projects. Now I will like to hand it over to Burt. And we also have our space forums. Our first space forum is going to be on May 22nd. And then on June 12th, we will have it just before the conference. It will be about the covering space launch history with Tom and Mark. And then we will resume our space forums in July. I will hand it over to Burt now. We'll start the program.
Thank you, Sadia. Very good. Thank you both so much. Thank you for joining us. We're looking forward to working with you as we move forward with all these space forums. So everybody, let me share my screen here. Oops, there we go. Let's get this out. Go. So welcome again, everybody. And I am Burt Dicht, as I said, Managing Director of Membership for a National Space Society. And I want to take you back about 53 years ago to April 20th, 1972. The Congress had just approved the NASA budget. And in that NASA budget was the development of the Space Shuttle program. Well, the next day, astronauts John Young and Charlie Duke are walking on the moon, and Mission Control radioed up to them and told them about the approval of the Space Shuttle program. John Young replied, "The country needs that shuttle mighty bad." Now, no one knew at the time that, John Young would be eventually commanding that very first flight of the Space Shuttle 9 years later. And he and Robert Crippen would usher in a completely new era for America's space program. So really exciting times. And of course, again, that's where my title is derived from, that moonwalk to the first space plane. And what I want to do tonight is talk not about the different shuttle missions, but my focus here is going to be on how the shuttle was developed, what led to its development, and also some of the challenges that were encountered. And then we'll also talk a little bit about the legacy of the shuttle as well. So when the shuttle program ended in July 2011, there were 30 years of operation of the space shuttle from 1981 to 2011, 135 flights. They spent 1,300 days in space, traveled 530 million miles, about average of about 4 million miles a mission, and delivered more than 3 million pounds to orbit. The space shuttle Atlantis landed at the Kennedy Space Center on July 21st, 2011, and that was the final flight of the space shuttle program. So the origins, it's interesting to know, most people probably don't realize it, but even before we landed on the moon, NASA was looking at different options for what we were going to do after the space shuttle, after the Apollo program. And they had a lot of grand ambitions, orbiting space stations, missions to Mars, even nuclear-powered spacecraft. But unfortunately, those ambitions ran directly into the political and financial realities of the time. The Nixon administration and Congress definitely supported a human spaceflight program. They just wanted a far less expensive version of it. Nixon was a really balanced budget advocate, and he really pushed for controlling spending. So what NASA had to do is they opted for a reusable space transportation system with the intent of lowering the cost of getting into space. Now let's go back even a little bit further. And as people started thinking about space travel, I'll take you back to 1954 to this issue of Collier's magazine. And in this magazine, Wernher von Braun was talking about different aspects of space travel. And you can see the image of a rotating space station. You can also see a winged spacecraft. Now, let's be honest, you don't need wings in space, right? So that must have been a space plane that would go back and forth between Earth and low Earth orbit and so on. And these amazing illustrations by Chesley Bonestell just give you a great sense of imagination of what space could be. So, but the idea for a reusable spacecraft obviously predates any of our efforts to get into space. And of course, the first artificial satellite, Sputnik, which was launched in 1957. But that didn't stop science fiction writers, that didn't stop Hollywood filmmakers who envisioned these winged rockets, and they would make repeated trips into space carrying people and cargo. And of course, one of my favorite space plane from Stanley Kubrick's classic film 2001, A Space Odyssey, the Pan Am Space Clipper. And I don't know if you've seen the movie recently, but I always like to watch the scene of the Pan Am Space Clipper flying through space, heading toward the space station with the blue Danube in the background. It made a lasting impression for me. But as an aerospace engineer, you say to yourself, well, that's a pretty nice space plane, but how does it actually work? You don't actually see how it got into orbit. And what's also interesting about this as an aerospace engineer, it has no vertical tail. So it must have some sophisticated flight control system that they thought of without having a vertical tail. But it just gives you the idea again, when you're making a movie or writing a story about space, you don't actually need to worry about actually pulling this off. And of course, doing something like this was well beyond our technology. And our early efforts at spaceflight, of course, were with ballistic missiles. The Mercury Redstone, the Mercury Atlas, the Gemini Titan, they were all ballistic missiles that were not reusable. Of course, they were expendable. But that is what the technology was in the late 1950s and early 1960s. Even the Soviets and their mighty R-7 rocket, which was also a ballistic missile, was way beyond, was far short of the capability of trying to do something reusable. But in response, of course, to the Cold War, we focused in on ballistic missiles, and they became those primary launchers for human spaceflight, both in the United States and the Soviet Union. It wasn't until, of course, the Saturn V where we had a rocket designed solely for the civilian space program. Now, when you talk about technology, sometimes technology advances real quickly. Sometimes it advances in stages that leads you to a new point and, the idea of doing something reusable. Well, there was a scientist at Ames Aeronautical Laboratory, part of NACA, the National Advisory Committee for Aeronautics. This was the predecessor to NASA. In 1952, his name H. Julian Allen, he was doing research, and he found out that use of a blunt body and also coming in the atmosphere at a high angle of attack during re-entry would produce a shock wave ahead of the vehicle, and that helped deflect some of the heat away. It was called the blunt body principle, and we started using that obviously on our initial spacecraft. The capsules had a blunt body bottom, and also you can see in some of the pictures there for re-entry vehicles for ballistic missiles as well. So that was one step forward in technology that helped us get to reusable spacecraft. Then, of course, you have the X-15 rocket, another rocket designed by NACA, built by North American Aviation, and of course flown by NASA eventually and the Air Force. The X-15 flew to over 260,000 feet into the edge of space, reached speeds of beyond Mach 5. They actually did 199 flights with the X-15. Now, it's interesting, the X-15 was dropped from a B-52 mothercraft, launched as a rocket. It used a reaction control system when it got into space, and re-entered the atmosphere as a blunt body and guided to a landing on a runway. Now, critical technologies involved in the X-15 included, an engine that you could throttle, and also that was reusable. But another important component was the reusable thermal protection system for the X-15. This was called a hot structure. The X-15 was made out of Inconel X, and that allowed it to handle the heat of reentry as it was coming back through the atmosphere. Just another step to get us to something reusable. Also, there was the X-20 Dinosaur, designed by the Air Force, and this was designed to conduct military missions. They would actually be flying into space and do what they called something dynamic soaring, skimming off the atmosphere and doing their mission and then coming back to land. Now, it's interesting that they named a project after a species that became extinct. I don't know whether that had anything to do with it, but the Dinosaur was canceled in 1963 before ever flying. But there was a lot of research done, and it benefited both NASA and the Air Force as well. So you had those three things: blunt body, you had the X-15, you had Dinosaur. All of those things helped advance technology and moving us to a reusable spacecraft. So let's go back to NASA now. As I mentioned, NASA leaders were looking toward the future of NASA after the Apollo missions. This is before we even had a successful Apollo mission. This is 1967. That is George Miller. He was the associate administrator for manned spaceflight at the time. And he was looking at different options for what NASA would do after the Apollo program. He proposed one program called the Apollo Applications Program. And this was eventually the Skylab program about conducting scientific research in space. So his initial work led to Skylab, but his thinking was also much longer term. And he thought about orbital space stations forming the foundation of a US space program. But to make that possible, you had to get launch costs down. Launches were very expensive. And he had a saying that he said, "No law says space must be expensive." Well, there was one law that maybe he wasn't paying attention to, and that was the law of gravity. Living in a gravity well as we do, it takes a lot of energy to get something to space. That makes space very difficult. But what Miller did, he organized a one-day symposium in December 1967, brought together a lot of industry leaders, and was trying to figure out what can we do to bring the costs down. And unfortunately, they didn't come to any conclusion, but it started the discussions going to help get us on the path to something reusable. Now, the question comes up, why should we go from an expendable rocket to maybe a space plane that's reusable? The Saturn V was a really great rocket, but the reality is too, when you're launching something like that, you're throwing it away. And people always use the analogy, what if a airline company flew a 747 from New York to London and then threw the 747 away? That's basically what they were doing with these rockets. But also, you have to look at what's inside NASA's culture. It evolved from NACA, which was about airplanes. The astronauts were military test pilots. Many of the managers and engineers were all trained as aeronautical engineers and evolved into aerospace engineers, but they still loved airplane. And of course, NASA's identity was about cutting-edge aerospace research and development. But in the end, when you start thinking about it, they also thought that splashing down in the ocean just wasn't as elegant as landing on a runway. So that was another reason to maybe think about going in favor of a space plane and getting away from capsule technology. Now, there was an independent solution that one of a great aerospace engineer, Max Hunter, was looking at the Lockheed Missile and Space Company. Hunter was one of those rare individuals who had experience as an engineer working on both aircraft. He worked in Douglas aircraft on the DC-6 and DC-7, and also was a chief designer for the Thor rocket program. So he had a really good idea of aircraft economics, but at the same time, an idea about rocket design. And like Miller, he thought we needed a low-cost approach. So he led this development of something called the Star Clipper. This was a reusable piloted spacecraft using what he called a 1.5 stage approach. You can see the Star Clipper in the center there. It's shaped like a lifting body, and then it had a wraparound drop tank. So the drop tank would drop off once it got to the point where it was heading into orbit. This Star Clipper was equipped with 3 1.5 million pound thrust engines. It gave people a lot of ideas that maybe something like this was actually doable. Lockheed never went forward with the Star Clipper, but Hunter had an incredible career at Lockheed Missile and Space. He retired in 1987, having worked on many, many distinguished programs. And actually in 1995, the National Space Society presented an award to him, the Von Braun Award, for all he did to contribute to creating a spacefaring civilization. So his work, while it didn't see an end, it contributed to the efforts to create something reusable. So back at NASA, Tom Paine becomes the NASA administrator in late 1968. And NASA's budget, if you look at NASA's budget peaked in 1965 and started to decline. That's because most of that upfront money for Apollo was on the development. As they started getting to hardware and the engineering stopped or was strictly reduced, things got less expensive. So NASA was dealing with a really steep decline in its budgets. But Paine was not deterred by this. He envisioned a really robust space program, and he too thought of space stations, space tugs, nuclear-powered spacecraft, and missions to Mars. But the reality of the Nixon administration, when it came into office in 1969, they actually proposed an almost 1/3 cut to NASA's budget. I know we're talking about things like that now, but that would have clearly shut down the human spaceflight program after the moon landings were over. So Mars, a space station, were completely out of reach. Paine, like Miller, realized that we had to bring down the costs if there was going to be a human spaceflight program. So the idea was, let's look at developing a reusable rocket, so we're not throwing something away each time we launched. And he backed George Miller's ideas of developing a low-cost launch option. And this took on great urgency now. So Miller, like Hunter, was also convinced that you could apply airline economics as a basis for modeling a reusable space transportation system. And he looked at a configuration that would have reusable and high performance and long life rocket engines. Now, modeling it, you say, after the X-15, a reusable rocket engine, a reusable thermal protection system, and of course, it needed a sophisticated onboard maintenance and check system, a great computer system to tell you that all your systems are operating normally and you're ready for launch. So with that kind of urging, he decided to unleash these ideas on our top aerospace companies. So he asked McDonnell Douglas, North American Rockwell, Lockheed, Martin Marietta, Grumman, to develop workable designs. I think I missed a slide there. Sorry about that. Before going to that, he actually asked NASA's chief designer, Maxime Vigée, to come up with a concept for this reusable spacecraft. So Vigée developed a fully reusable two-stage configuration. It included a booster rocket that carried a winged orbiter on its back. The booster would carry the rocket to staging velocity and then would drop off and be piloted back to a runway to be launched again. The orbiter, as you can see, was rounded. I say it looks like maybe a slightly overweight X-15. It had straight and unswept wings, but it would continue to climb to orbit and then land on a runway after re-entry. So with this configuration in mind, Miller asked the McDonnell Douglas, North American, Lockheed, Martin Marietta, Grumman to come up with a workable design for Vigée's concept. There were enormous engineering challenges, but it was reality, the economics would shape the planning and design far more than the technical needs would. So a fully reusable system was going to be expensive. It's going to cost probably about $10 billion to develop. That's about $92 billion in today's dollars. So was such a system worth this cost of development? So they had to do a lot of economic cost comparisons here. And in doing their budget assessments, economists would be comparing a new shuttle system against the cost of using expendable rockets for a similar number of launches. So they really hoped that the initial shuttle cost estimates would be about $100 per pound. Compare that to a Saturn V at the time, which was about $1,000 per pound and about $185 million to launch. The target launch cost for a shuttle system would be about $10 million. And that compared pretty favorably to $25 million for an Atlas Centaur, maybe about $15 million for a Delta. Those were the two main expendable rockets at the time. And these costs are all in $1975. Now, the trade-off for a reusable system was it costs you a lot more to develop, but the launch costs are less. But would there be enough flights to justify the high development costs? So I want you to think about an analogy here. When the Prius car came out, the hybrid, those cars cost about $5,000 to $6,000 more than a car in a similar class that was gasoline powered. So are you willing to spend that extra $6,000? Well, your goal might be, I'm doing it because I want to save a lot of money in paying for gas. But you have to do the analysis. Okay, I'm going to pay $6,000 more. Will I drive enough? How many miles am I going to drive and how many gallons am I going to use over the course of this car's life? Will it pay for itself in order to make it worthwhile to spend all that extra money? So they were looking at the same idea here. Is it going to be worth spending all that extra money to develop this instead of just using expendable rockets? And I just wanted to put in there as a note the A SpaceX Falcon 9 today launch costs about $52 million. That's about $6 million in 1968 dollars. So big difference. But with that idea in mind, what they started to do was they looked at how many launches could you anticipate over the course of maybe a 15-year life for the space shuttle program. And they came up with, and they tried, honestly, you're not in being able to envision new things. Like today, with lower costs, a lot more people are putting things into space than they ever would have dreamed of. But they were just trying to base it on what they knew at the time and what the idea would be. So they needed somewhere between a minimum of 500 launches over the course of the program, or even up to 900, which is almost one flight a week, in order for it to justify spending all that extra money. But even with the most optimistic view of commercial missions, the operational life, there just was not enough there were not enough launches to justify spending all that extra money on the program. So Thomas Paine needed a partner. And with a large manifest, he turned to the US Air Force as a primary customer. They launched a lot of satellites into space. Paine went to them and said the shuttle would be available for any of its needs. Now, that, of course, drove a lot of things. And there was a question that was submitted about this, about should NASA have allowed the Air Force to dictate the design? Well, NASA went to the Air Force and said, we want you as a partner. So if that was going to happen, they had to meet the Air Force's requirements. So it wasn't like the Air Force was dictating to them. The Air Force said, hey, if you want to launch our payloads, this is what you have to do. So they had heavy payloads. They wanted 65,000 pounds to go to orbit and about 30,000 pounds to go to polar orbit. They also needed a payload bay of 15 by 60 feet to accommodate the largest reconnaissance satellites. The keyhole optical reconnaissance satellites were about the size of the Hubble Space Telescope. These were large, and they needed a payload bay to accommodate them. So this meant that the design that Maxime Vigée came up with just wouldn't fit it. They needed a much larger orbiter than was originally planned. There was also one other requirement that the Air Force had, and that was for these polar orbit missions. And that required something called cross-rangeability. So think about it. If you're doing a polar orbit, the Earth is rotating from west to east, and so you're going to come back to the same latitude during your re-entry that you had from the liftoff. But because the Earth is rotating west to east, your landing site is moving, and it's going to be almost 1,000 miles away by the time you get back from orbit. So they needed this ability to fly about 1,200 miles cross range to the landing site after a polar mission. And Vigée's straight wing configuration just wasn't going to cut it. It only had a range of about 230 miles. So what they really needed was a delta wing. It had much more surface area. Of course, you had to cover that surface area with thermal protection. But Vigée really fought that. He really wanted to keep the design simple and fought the delta wing. But the reality was, in the aerodynamics side, the delta wing was actually better performing through the broad Mach ranges that the orbiter would see when it came back from space and guided to and landed at a runway. So you had two things happening. The size and the delta wing were two key components that changed the whole design of the orbiter. So one of the things that Paine also needed was he needed a stronger case to go to Congress. And what are we doing with the shuttle? Is it just a truck that's going to take things to orbit? And he needed an ability to say, no, we're going to do a lot more with the space shuttle. And so he asked an Apollo manager named Leroy Day. Leroy Day was working on Apollo 10 at the time. So this is in April 1969. And he asked Leroy Day to take a lead role in the shuttle development. And he wanted him to look at what could the shuttle do besides just carry cargo. And some of the things, he came up with a long list. Some of the things included satellite repair and checkout, actually retrieving a disabled satellite, carrying laboratories in the payload bay to do scientific research. All of these were really critical selling points to NASA. And the fact that the shuttle would accomplish all of these things is really a testament to Day's engineering foresight. So with all of that worked together, they had an idea on a concept, but you still had this issue of a $10 billion cost to develop a reusable system. And that was just way too much money for the Nixon administration. So over the next 2 years, NASA and aerospace contractors were conducting hundreds of feasibility studies to determine the practical configurations. And at the same time, the economists at the OMB, the Office of Management and Budget, were evaluating the cost estimates and kept insisting that NASA had to do this with $5 billion, less than half of what they requested in terms of developing this completely new system. So 10 billion to 5 billion. And here are just some of the concepts some of the companies were working on at the time. Some of them included air-breathing engines, fully reusable two-stage concepts, and so on. But still, the cost was beyond what they were going to be able to get from both the Nixon administration and probably from Congress as well. One of the things they did to simplify this was made a decision to make the orbiter a glider. So why not equip the space shuttle with air-breathing engines and set them, and use that? But the idea of a glider actually resulted in great complex trade-offs. Okay, weight, complexity, safety, and mission requirements. Think about an air-breathing engine. Now, obviously, it needs fuel. They're heavy. You need air intakes and a lot of associated systems. So that's going to add a lot of weight and complexity to the spacecraft, which means you obviously can't take as much payload into space. Then you have to think about thermal protection and safety itself. When the shuttle comes back, it reaches temperatures anywhere from 1200 to 2700 degrees Fahrenheit. How do you protect that engine? It couldn't just stand out like it does on an airplane. It has to be either designed to take those temperatures or be hidden behind some protective doors. And if it was hidden behind doors, then at some point it's going to have to deploy and you're going to have to start those engines up. And what if you can't do that? And that could risk losing the whole space shuttle at the time. So the idea was, let's make the design as simple as possible and not try to have these flyback boosters, turbojets. They were dropped. NASA prioritized reusability and operational efficiency. And they focused the shuttle as a space transport system, not a long-range atmospheric flyer. That's just a glider. So they were really confident based on experience with the X-15. There was a lot of experience with the lifting bodies that gliding to a landing was an effective approach. It is just a case, as any pilot will tell you, of energy management, managing the potential energy, that's the altitude, and managing the kinetic energy, the airspeed. And I don't know if any of you went to an air show many, many years ago. You saw a guy named Bob Hoover. And Bob Hoover flew with Chuck Yeager, and he became a really great air show pilot, flying the P-51. And he flew something called a Shrike Commander, which was a business aircraft designed by North American Rockwell. And what Bob Hoover would do, and this was always amazing, he'd be flying the airplane doing aerobatics in a plane not designed for aerobatics, and then he would turn the engines off in the air. He would continue to fly the aircraft, doing maneuvers, including loops, then land on the runway, excuse me, and then cut a ribbon. And it was incredible. And he said this was energy management at its best. And he actually did this as a tribute to the space shuttle because he worked for Rockwell. So they really believed that the glider was going to work. But still, what do you do about the budget? So NASA followed Hunter's Star Clipper lead and decided to go with a drop tank for the liquid hydrogen and liquid oxygen that would power the orbiter's engines. This reduced the cost to about $8 billion. It was still too high. Really, the most expensive component of the initial system to make it fully reusable was this booster rocket. And it was going to have to be large now that the shuttle was larger. It was about the size of a 747. And when you think about it, the 747 is the shuttle carrier aircraft. It had wings, it had rocket engines for liftoffs, and jet engines to return to a landing site. It was really complex. I don't even know if they could have pulled it off technologically. But there was another option. And Tom Paine had enlisted the help of a company called Mathematica. This was a consulting firm, and he wanted NASA to conduct its own financial analysis. You know, obviously the OMB was doing this, but Klaus Heiss, who was an economist working for Mathematica, actually pushed a concept called Thrust-Assisted Orbital Shuttle, or TAOS. Now, he's not an engineer, he was an economist, but he saw this concept, and he thought this would be cheaper to develop than this big rocket that they were planning to use. So it used the orbiter itself, used an external tank, and now instead of this big rocket first lifting stage, they were going to use two booster rockets. So at liftoff, the orbiter's engines and the booster rockets would ignite and take the orbiter up, and the booster rockets would drop off, be recovered and refurbished and reused. The estimated cost for this program was $5.5 billion. Getting closer to what the Nixon administration was offering NASA. Well, Paine left NASA and James Fletcher took over as the administrator in 1971. And he made the final decision to go with the TAOS shuttle. But they still needed another $500 million. And this is where George Shultz, who was the OMB director, came in. And he believed the United States could afford a space program. So he fought to get the extra $500 million from the Nixon administration. And NASA had its $5.5 billion to design the shuttle. So on January 5th, President Nixon announced the start of the shuttle program. He said it was going to revolutionize transportation in near space by routinizing it. It will take the astronomical costs out of astronautics. And finally, on March 5th, 1972, NASA announced the final shuttle configuration. It consisted of this reusable delta wing orbiter, about the size of a DC-9, with that 15 by 60 foot payload bay, and partly reusable solid rocket boosters, and an expendable external tank. So it's the shuttle that we know today. But what's interesting about this is that as engineers, we know, sometimes you're trying to design something completely new, so you're trying to come up with a budget and around what it would really take to design it. This is not how the space shuttle was designed. They were given an amount and had to figure out how to build it with that amount, not the other way around, not the typical best way to do something so ambitious as the shuttle program. So the objectives, of course, a goal of a first flight in 1979. Of course, again, Congress approved this in April of 1972 when John Young and Charlie Duke were on the moon. The idea was low-cost access to space, about a $10 million per flight, about $100 per pound. The goal was 55 flights a year, turnaround time of about 2 weeks between flights. The system, of course, needed these high-performance and long-life rocket engines. It needed a reusable thermal protection system and a sophisticated onboard computer. But the reality really was they were pushing the boundaries of technology and designing a reusable space transportation system would actually be more difficult than it was to go to the moon, technically. And they were going to soon find that out. And two of the areas that gave the most trouble were the rocket engines and the reusable thermal protection system. Those would really challenge designers. So the shuttle's main engines, which were called RS-25s, the main contractor was Rocketdyne. And Rocketdyne built the F-1, built the J-2 that took us to the moon. These rocket engines, about 375,000 pounds at sea level, about 470,000 pounds of thrust in the vacuum of space. The throttle range was 65% to 109%, and an operational life of about 27,000 seconds. That was about, again, firing for 8.5 minutes, 55 flights. The challenge, of course, with cryogenic fuels that they were using, you have super cold liquid hydrogen and oxygen being fed in at minus 400 degrees Fahrenheit. And then they combust at around 6,000 degrees Fahrenheit. Very challenging, of course. But one of the more interesting aspects of this was the high pressure turbo pumps that they used, that they were planning. 75,000 horsepower. And these fed the fuel and oxidizer. They were about the size of outboard engines, yet they rotated at almost 24,000 RPM. Can you imagine one of those on your boat? If they're the size of, let's say, as an outboard motor. But they really thought they could come up with a reusable engine. You know, Rocketdyne did the J-2. The J-2, if you recall, after the S-4B got into orbit, they had to actually refire the J-2 in order to do translunar injection to get to 25,000 miles an hour to go to the moon. So Rocketdyne thought, oh, you know, we've had an engine that we reused, but they had no idea that this one was going to be so difficult. Extreme temperature, pressures, the spinning speeds resulted in many, many failures during the testing program. Engines were blowing up. Rocketdyne engineers actually had to go outside the company. They got help from leading researchers and leading universities and laboratories. And in the end, excuse me here, they had to develop new materials and manufacturing processes in order to make the rocket engine work. They had a rigorous testing program, 726 hot fire tests, totaling more than 110,000 seconds. And remember, the whole life of this engine would be 27,000 seconds. So almost 4 times as much testing time than the entire life of the engine itself. But in the end, the engines themselves proved to be pretty reliable. And of course, they're using the leftover RS-25 engines on the Space Launch System now, 4 of those on each mission. But now they're obviously not reused. They're going to be thrown away each time. But it was very hard, and it slowed the program down. The other slowdown was this thermal protection system. And how do you control the heat of reentry? Of course, the Apollo program, Apollo's capsule were coming back at 25,000 miles an hour. So that was much harder than the Mercury and Gemini capsules. But those spacecraft used something called an ablative heat shield. An ablative heat shield reacts with there's a chemical reaction when it reacts with the heat. And then the material breaks off and disperses the heat as it flies away from the spacecraft. It's a great system, but it's not reusable. At the time, we didn't have a reusable ablative system. They thought about, well, what about using a hot structure? You know, like the X-15 had Inconel X. What if we use titanium? The SR-71, of course, used titanium, and that's all temperatures of about 600 degrees. Titanium actually melts at over 3,000 degrees, but really they had no real experience with that in terms of creating an aircraft skin. It's very hard to work with. And it also was not suitable for sustained high temperatures. It weakens after continued exposure to high temperature. So that isn't going to work. Plus, it was not a very good insulator. So the heat is going to get through. So those things, you cross off ablative, you cross off hot structure, and the idea then moved to something that Lockheed Missile and Space came up with called reusable surface insulation. And these were tiles made of silica, and they're actually 90% air by density. They could withstand temperatures of up to 2,300 degrees Fahrenheit. The hottest areas, by the way, of the orbiter when it comes back are the nose cone and the leading edges, and those are made of reinforced carbon-carbon, which again has even has a better temperature strength than the tiles themselves. But RSI, the challenge of them was that you had a large area to cover. So that meant on Columbia, the first orbiter, almost 30,000 tiles. And here's the thing, no two were alike. They had to be bonded to the skin by hand, very close tolerances. Even when they flew Columbia from Palmdale to Kennedy Space Center, 7,500 tiles came off or were damaged. Certainly not going to handle flying through space, flying, and coming back through the atmosphere if that happens on just a trip to the Kennedy Space Center. What was happening was the aluminum skin would flex, and it was kind of popping the tiles off. They went to DuPont. DuPont had a system of coating called Ludex, and these were actually applied before the tile was adhesive to the orbiter skin, and it reinforced the tile strength. But like the engines, it took about 20 extra months of round-the-clock work to solve this adhesive problem and get the tiles in place. And thinking about today, the Starship uses about 18,000 tiles, but they're hexagonal tiles in shape, so they eliminate the straight edge, which might cause bleed, and also they are bolted on to Starship, not adhesive, and that makes them much stronger. So they're made of ceramic and metallic alloys, so they've made a lot of advances in that. But this is what they chose for the orbiter at the time, and it was a hard thing to do. And just to give you an idea of Discovery, which is at the Udvar Hazy Museum, Discovery had 24,000 tiles. About 20,000 tiles are original. So over the course of all its flights, they had to replace about 4,000 tiles. And after each mission, every tile had to be inspected. So very time consuming. That's Columbia as it looked when it arrived at the Kennedy Space Center after leaving its factory in Palmdale. So the shuttle stack. I don't need to, I'm sure everybody is aware of that. The two solid rocket boosters, the external tank, the orbiter. It took 9 years, again, April 1972 to April 1981 to get the shuttle launched, longer than it took us to achieve the first moon landing. Kennedy gave us the speech in May of 1961, and we landed on the moon in July of 1969, 8 years. So it took a little longer. These are the solid rocket boosters that you see. They're about 1.4 million pounds of thrust each. They burn for 2 minutes. Of course, about Challenger, because the rockets are assembled in segments with O-rings in between to protect them. But the propellant itself is aluminum powder. The oxidizer is ammonium perchlorate, and they have the texture of a pencil eraser. The challenge, of course, of solid rockets is that once you fire them, there is no way to stop them, and you can't throttle them as well. So these were designed, solid rockets were designed for the ballistic missile program, the Minuteman missile, made it perfect for something like that. But this was the first time we were proposing launching humans using solid rockets. And now the Atlas V that launched Starliner does use 2 small solid rocket motors. The solid rocket boosters could be used approximately 25 times. The external tank, the only piece that's thrown away, Again, about 146,000 gallons of liquid oxygen, 400,000 gallons of liquid hydrogen. I know they had looked at different ideas to use the external tank as possibly a space station, but they never got around to doing anything like that. So it was the only piece that was thrown away. The orbiter itself, designed by Rockwell Space Transportation Systems Division, a big vehicle, 122 feet long, 78 feet wingspan, 58 feet in height, about 150,000 pounds empty, and a gross liftoff weight of about 240,000 pounds, depending on what was in the payload. Operationally, about 100 to 400 miles. As you saw, the rocket engines were for 55 flights. The solid rocket boosters, 25 flights. The structure of the orbiter was designed for 100 flights. So it actually could last a lot longer than the engines or the solid rocket boosters. And you know the profile, about 6 seconds before liftoff, the shuttle's main engines ignite, make sure they're operating correctly. Then the solid rocket boosters ignite. About 2 minutes after liftoff, they dropped off, landed in the ocean, recovered, and were refilled. 8.5 minutes after liftoff, the orbiter is in orbit. The external tank is discarded. They do their operations, and then they come back through the atmosphere and land on a runway. So we all know that well. These are the 6 orbiters were built, and I'll talk about where they are in just a few minutes. But Enterprise, of course, was the prototype. And Columbia and Challenger were the first 2. Discovery, Atlantis, and then Endeavour was manufactured after the Columbia accident. And again, we'll talk about each of those in a second. It's hard not to talk about the shuttle without the 2 tragedies. Challenger on January 28th, 1986, caused by the O-ring erosion, and Columbia on February 1st, 2003, caused by a piece of insulation that struck the reinforced carbon-carbon panel of the left wing. 2 very avoidable accidents, and there's obviously a lot that was said about each of these. And obviously the shuttle legacy has these 2 accidents and the loss of 14 astronauts. But astronaut Mike Mullane, who in his book, Riding Rockets, talked about something called the normalization of deviance. Now, he did not come up with that term, but what it meant was that you have a design parameter, and then you put something through its operation, and you start looking at it. How well did it perform? And you say, oh boy, it didn't actually perform as well as we expected, but we're going to basically turn that into the new normal. And that's really what happened with both the SRBs and the external tank insulation. The O-ring, they noticed O-ring erosion frequently and realized that, the first O-ring was eroding. The second one there kept the orbiter protected. But no one said, let's fix this right now. They said, well, it's operating. It's kind of our new normal. And the same with the external tank. Insulation was falling off the tank in previous flights, and nothing bad happened. They said, well, it's a problem, but it's not going to cause a problem. So that became a new normal as well. And as you're looking at human spaceflight, we got to avoid the normalization of deviance. It's just, and we'll talk a little bit about, was the shuttle a flawed design? But these 2 tragedies were just horrific. There were also some questions about the cost, about the whole program. Someone did ask about how much a single orbiter cost. The best information is on Endeavour, because that one was added in at the end. So that was close to $2.2 billion it cost to actually build it. Obviously, all the engineering is done for that. Total shuttle development. Remember, we talked about $5.5 billion. Well, it actually turned out to cost $10.6 billion to design the whole shuttle system and get us to that first launch. The total program cost between 1972 with go-ahead to the end of the program in 2011 was $174 billion. And these are then year dollars. These are not adjusted to inflation. These are how much things actually cost. So when you divide 135 flights into 174 billion, you get about $1.3 billion a launch, a lot more than the $10 million estimate that they had at $100 a pound. So it certainly did not get anywhere near what they anticipated in terms of operations. A lot of accomplishments. I won't spend too much time here, but obviously the first reusable, crewed spacecraft, lots of satellite deployments and even satellite repair, including like Solar Maximum satellite, deploying the Hubble Space Telescope and repairing that, actually allowing for the construction of the International Space Station. There were space labs, space hab missions, a lot of scientific research itself on the shuttle, a lot of firsts in terms of diversity. Sally Ride, Guy Bluford, a lot of international astronauts. It supported international missions like Chandra X-ray Observatory, and it did spacecraft retrievals, just like Leroy Day envisioned. There were military missions and a lot of technological demonstrations. It was an impressive program over the course of the 30 years. But what about it? Is it a flawed design? Nixon, in announcing the shuttle program, said we wanted to make flying into space routine. But the reality, after 60 years of human spaceflight and the loss of Challenger, Columbia, we realized that launching humans into space is hard, as they say. I know a lot of people think it's a cliche, but when you have to put that much energy together to get something to go 17,500 miles an hour, you don't leave any room for error. And while the shuttle was a remarkable flying machine, a rocket, a spacecraft, a glider, all in one, it just never lived up to the goals of an airline-type operation with low operating costs. The original cost estimates were based on turnarounds of 2 weeks, economies of scale of 55 flights, which brings a lot of things down, but never achieved more than 9 flights in a year. And that was 1985. It was an incredibly complex machine that required a lot of support infrastructure, both in facilities and people. There were 10,000 people at the Kennedy Space Center who processed the orbiters and the shuttle system to get those from when it returned to get it ready for another launch. But the real flaw, obviously, with the 2 accidents was the lack of a robust escape system was recognized as a significant and tragic oversight in the shuttle's design. And one thing I always ask as I look through the literature, especially when the initial idea of the shuttle to carry satellites and transport them into space instead of using expendable rockets, did anyone actually say, should we really risk human life to just launch a satellite? It's one thing if we're going up to repair, it's another thing if we're going up to assemble the space station, but just to launch a satellite, should we risk human life? And I don't know of anyone, I haven't seen anything in the literature where people actually question that. And so a really important question as you look at the orbiters and the shuttle program. As I wind down here again, President Bush, Bush 43, unveiled a vision for space in 2004. And at that point, they made the decision to retire the space shuttle as soon as the International Space Station was assembled. And of course, that happened in 2011. In looking back at shuttle, it's clear they oversold its capabilities and underestimated its technical challenges and cost. Of course, they had nothing to base their estimates on. Trying to come up with something brand new, something that didn't exist, and doing it on a shoestring budget made it very, very difficult. But my final take on it is they had great innovation, great persistence, great dedication. They created an incredible vehicle that carried, at the time, 70% of the 550 plus individuals who've gone to space. That's orbit, not low Earth orbit. Launched more than 100 payloads, and as I said before, took 3 million pounds to space. A pretty impressive legacy. I got to see my only shuttle launch in November 2009. I did go to one before that, and it didn't go. And as the shuttle was retired, the Aviation Week asked this question, was the space shuttle worth it? So this was July 2011. So I wrote a letter to the editor for Aviation Week, and I'll just read it real fast here. I saw my one and only shuttle launch in November 2009 as Atlantis lifted off as part of STS-129. I will always remember the spectacular sight as Atlantis climbed to orbit, but just as ingrained in my memory was the sound of thousands cheering her on. A sense of pride washed over me. As an engineer, I know the technical genius it took to develop such a vehicle, but I was even prouder of being an American, where dreams like the shuttle program can be made possible. So in answer to the question posed on a recent cover, was the space shuttle worth it? I would have to say a resounding yes. Over time, I'm confident the shuttle's contributions to the nation, technology, engineering, and science will be viewed positively. Its true worth, however, extends beyond tangible benefits. The shuttle was the result of visionaries who dreamed of big things in space, but the budget realities of the time limited them to low Earth orbit. Enormous technological challenges were met on a shoestring budget, and an incredible flying machine emerged. The shuttle represented the best aspects of the US, the ability to dream and achieve amazing things. With its ending and the recent fractious budget displays in Washington, I just hope those days have not passed us by. Fractious budget displays, in Washington. I guess we're not seeing any of that anymore, right? So, but it was my own tribute to the shuttle program. And if in case you're wondering and want to try to visit them today, the Enterprise is at the Intrepid Sea, Air, and Space Museum in New York City. I used to be a volunteer there, and I was there when the day it arrived at the John F. Kennedy Airport. And you see a picture of it on the Intrepid there before they built the shuttle pavilion around it. So you get a chance to see Enterprise, go up to New York City, let me know and I can get you in. Discovery is at the Udvar-Hazy Center in Chantilly, Virginia, outside of Dulles Airport. And that's the most flown shuttle. And here, of course, where I am in Florida, Atlantis at the Kennedy Space Center Visitor Complex. I was treated to a day when they rolled Atlantis over to the new shuttle, the Atlantis Pavilion. You could actually see it inside the pavilion before they started working on it there, and of course what it looks like today. I definitely recommend it. If you're coming to visit, let me know, and I'll escort you in as to see Atlantis. Now, Endeavour, that is an interesting one. Endeavour is at the California Science Center in Los Angeles. There's me back in 2019, but Endeavour is no longer available for display right now. They are creating a whole new display where it is going to be organized as the vertical stack that we know. This is going to be an incredible display. I was out there last May for ISDC, got a chance to see some of the assembly that they're doing. It is now fully enclosed. What you're seeing there on that top picture is the orbiter wrapped in a ballistic cover that was to protect it in case something dropped or so on as they were doing construction. It's now completely enclosed, and this is supposed to open around early 2027, and I will be sure to be there when it does. It's just going to be a magnificent display. Just as a closing point here, I know people were talking about space planes. Of course, today, the X-37, which is operated by the Space Force and is very classified, has been making many trips into space, about 400 days at a time. One just flew and landed back in March. It's not crewed. It's U.S. national security, of course, and uses a runway landing. There's the Dream Chaser, which is at the Kennedy Space Center now in checkout. Its operator is going to be Sierra Space. They're targeting a launch for late 2025. It is going to take ISS cargo up, but it eventually will be crew capable and also do a runway landing. The first launch is going to be on an Atlas V, and I believe then it's going to transition to the Vulcan. The Chinese now have a space plane called the Shenlong, and it's done a couple of tests. It's shrouded, of course, in secrecy, figuring from China, but it's near space, reusable. And you might say it looks a lot like our X-37. And one that's really ambitious is called the Radiant 1. It's in development by Radiant Aerospace. This is a single stage to orbit. It'll launch horizontally and land that way, rapid reuse every 48 hours. It actually will launch on a rail, a 2-mile long rail, and take passengers and some cargo up to the space. So that would be really interesting. The European Space Agency is working on something as well. So we'll see where Spaceplanes go. And I close out. If you have any questions about some of these, I encourage you to take a look at some of these books. A Great History by T.A. Heppenheimer on the Space Shuttle decision. Space Shuttle celebrating 30 years. A Space Shuttle Developing an Icon. 2 great books by John Logsdon on After Apollo, some of the decisions from the Nixon administration, and the Space Shuttle Legacy and What We Did and What We Learned by Roger Lanius, the former NASA historian. And then a new book by Tom Jones, which looks at every flight firsthand by astronauts. Fabulous book. I highly recommend it. I will be glad to send this out to anybody who'd like a copy. I'll probably just do that to all the attendees. And this is also based on an article I wrote for Mechanical Engineering magazine back in 2011, July 2011. I'll be glad to include that as well. So thanks for the opportunity. I know I spoke for a long time. It was getting to my throat, but now we hopefully can answer some questions. So thanks so much. Let's turn it back over to Sadia and to Stephanie.
Yeah. So I have here some questions that people have posted before
Okay.
joining, and let's go through them. One of them is, at what point did NASA or the federal government know that the shuttle wasn't going to live up to its original vision?
That's a good question. I think they knew pretty fast once it became operational that it really required a lot of inspections, a lot of potential maintenance. So I believe they knew very early on in the program that it was never going to achieve a flight every 2 weeks. Now that doesn't mean they didn't consider things a success, but it was a very complex vehicle, and I think they realized it pretty fast.
Thank you so much. So our next question is, how much have space shuttle disasters contributed to the culture of safety in NASA?
I think it's contributed a lot. They had an increased culture of safety after Columbia. I'm sorry, after Challenger, but I think it really solidified after Columbia. And the most recent launch of Starliner was a good example of that. Boeing, of course, thought that the Starliner was safe to come back from the space station with Butch and Sonny, but NASA erred on a very conservative approach and decided to, let them stay on board, come back on a SpaceX Dragon, and figure out what we can do with the Starliner after that. So I think today that culture of safety is really very prevalent throughout NASA, and I think the companies that are going to be doing human spaceflight, you realize a tragedy. Certainly things can happen, but I think they're going to try to do everything they can to make sure these missions are as safe as possible.
Perfect. So now I have some questions for about the administration, and how does the organization feel about the current administration's NASA's budget?
A good question. Obviously, I can't speak for NSS itself. I'm not involved in the policy committee, but there is great concern about the cuts to especially the science directorate and the missions that could be canceled from that. Obviously, we like to see human spaceflight, but we really don't know what this means for what happens to go back to the moon if they do decide to end Artemis after the 3rd mission. But I think we also recognize, or I recognize, that $4 billion is a lot of money for each launch. We're talking $1.3 billion for a shuttle. So $4 billion for an SLS Artemis launch is a lot of money. So I think we have to really think about those things. NSS is not taking the same approach as the Planetary Society. It's taking a more measured approach at this point to wait and see what the actual budget proposal is when it's submitted to Congress. and how how Congress will react to it. But they did. If anyone is interested, if you go onto NSS.org, there is a press release from NSS on the science directorate cuts and the concern that presents. So I think it was done April 28th, something like that. So I would encourage people to take a look at that, and I think you'll be hearing more from NSS as we see more about the budget.
Stephanie, do you want to take some questions?
Yeah, we got a few questions in the chat, and I just want to shout out there was great conversation in the chat function. So thank you to everyone who was sharing their experience, their knowledge. It was awesome to read. But why didn't NASA develop and modernize the shuttle program, or are you aware of any plans to do so?
No, I mean the shuttle program is officially over. There is no going back with it ending in 2011. The orbiters now belong to the museums that have them. The one in Udvar Hazy is still owned by the government, but all the others, Intrepid owns Enterprise. The Kennedy Space Center Visitor Complex owns Atlantis, and the California Science Center owns Endeavor. So there's no way those will ever fly again. The reason they decided to cancel the program, and again, this was President Bush and his team, and it was a recommendation from the Columbia Accident Investigation Board that it was just too dangerous for the astronauts. That with no way to get out, with 2 accidents, they decided let us just make sure that we get the International Space Station built. And they also at the time wanted the requirement that anytime a shuttle launched, it had to actually dock with the space station. And that was in case there was some damage from the thermal protection system from the installation. The only time they did not go back to the space station was the final Hubble repair. And there was a lot of debate about that. Initially, the NASA administrators said, no, we're not going to launch it. But then there was an outcry, and they went up and did the last Hubble repair. Because once you're doing that, there's no way to get to the space station. There's just not enough fuel in the shuttle's orbital maneuvering systems to change orbits like that. So the decision was made back in 2004 to end it when the space station was finished, and no plans to do anything similar to that in the future at this point.
Got it. Along that same kind of thought process, Dave Ginsburg asked, what capabilities do you think we are missing by not having the space shuttle any longer? How can we get them back?
Well, I think a couple of things are the Hubble itself. There's talk about how can we extend the length of the Hubble Space Telescope. And I know that SpaceX was looking at some options, but without an ability to capture it and hold it in the payload bay and have astronauts work on it, anything to do another repair would be very difficult. So that's one aspect. Then of course, what to do with the International Space Station, how to handle that. So there are certain things, taking big payloads to space that require humans, orbital repair. But for what we are now with low Earth orbit and the space station, at this point, it's not being missed, but it might be as we look at replacing the International Space Station.
Yeah, that was a great question, Dave.
Yes.
And one more question I pulled from the chat, and then Sadi, I'll toss it back to you. What do you think was the single greatest accomplishment made by the shuttle in its 30 years of flight? From Mr. Jeff Fitzsimmons.
Wow, that's a tough one.
We got some good ones tonight.
I think the biggest contribution was that it allowed so many people to fly to space. I mean, there's a lot to be said for all the technological accomplishments, but when you're taking up 7 people at a time, it gave enormous ability to get people into space and have experience in space. And I don't remember how many different countries flew on the orbiter, but we took a lot of people who weren't from the United States onto the shuttle as well. And even non-professional astronauts, they were called payload specialists, went up. So my feeling is the human aspect of it. And, right now, yeah, I think that statistic that when the shuttle was retired in 2011, about 550 people flew in space. Okay. So it's been, what's it been now? 14 years since it retired. And we've only increased the number of people who float in space by about 100. It's about 650 now or something close to that. So it gave people a great ability to get to space. And I think I'm going to put that ahead of the technological achievements.
I love that.
Yeah, I have some questions in the QA section, and it says, "What from Jeff? What do you think was the single greatest accomplishment made by the shuttle in its 30 years of flight?"
Oh, I just answered that one.
Oh, that was okay.
That was the one I just answered. Yep.
Yeah.
I said the human aspect of it.
Yeah, thank you. Then I have some membership questions for you. So
Sure.
how can we help expand NSS engagement with the global space community?
Well, I think we're trying to do that now with some of the things that we're doing on the student side, actually. And I think you were a Spun Debate member, right, at one point. We're engaging lots and lots of students from around the world in our student competitions. And these individuals are going to go to college. They're going to be engineers. They're going to be, they're going to be future leaders, hopefully. And I think it's starting it at the ground up to try to have that kind of influence. And I think we'll have a lot of ambassadors going forward. I think that's a key component of what we're doing. I think we also have to look at it from, I know we're called the National Space Society, but we go by NSS. And I think we have to really embrace the fact there are, I believe, 70 countries around the world that have space programs. And I think we have to do more to tell those stories. We did a space forum a few years ago, and we should go back and look at that, about what they were doing in India with their space program. They have a pretty robust space program. And I think we should highlight some of these other space programs that are happening around the world. And I think that kind of engagement will have a big influence, because I think people are dreaming of going to space, and I think we can play a pretty critical role. And so I'm glad that question was asked.
Nice. Then we have an interesting question. Does anything from these talks on Zoom with NSS bring some projects from idea to reality?
That's a good question. Not in every case. We are trying to highlight, a lot of times, like today, we're doing history. We've done things like that before. But we do highlight some key technologies. We had a great talk, a very technical talk on a space elevator earlier this year, or last year it was. So we are doing things that are highlighting the progress we're making. But the space forums themselves are not meant to do that. Maybe we're trying to create an awareness of what's going on and help those individuals who are sharing these great ideas, so we can get the word out a little better. So I think we really have to do more of that, and because there's so many great ideas and things that are happening. Like next week, we're going to have someone from Firefly Aerospace to talk about Blue Ghost. So there's an example of the newest technologies. So we're looking forward to that.
Right. So another thing, how can someone become a member, and can anyone join NSS as a study program?
Well, we don't have any kind of study program, unfortunately. NSS is a member, we're an advocacy, a space advocacy organization. So we promote the settlement, I'm sorry, the exploration, the development and settlement of space. So that's our real goal. In terms of membership, we welcome everybody to join. If anybody is interested, I will definitely, for anyone who's on the call who's not a member, we can offer you a special $29.95 introductory rate. just reach out to me and I would be glad to, you have my email, reach out to me and I'll be glad to send you all that information. Or you can just go directly to nss.org and you'll see a sign that says join NSS, and you can join online. But reach out to me and I'll help you, make it a little easier for you. And we'd really like to have new members. That's why one of the reasons we're doing this Rising Stars thing at ISDC is to really showcase university students and early career engineers because they're the future, and we want to get them involved in NSS as well.
I will hand it over to Stephanie.
Okay. I know let's see, let's go to about 10:30.
Yes.
Still have about 70 people on.
We got a few cool ones coming in late too.
Okay.
There have been suggestions about canceling SLS and replacing it with Starship. How do you feel about such proposals, considering that Starship doesn't have a real timeline to being a functional vehicle?
I personally want us to get back to the moon. I think we have to get back to the moon before China does. China has a very sustained, deliberate space program, and they are working their way to do that. I think we need to go back there and get there before anyone else. And right now, right now, SLS offers the best approach to do that. Now, Starship's already a component of Artemis because they're building one of the lunar landers along with Blue Origin. So Starship is already gonna play a part in getting us back to the moon. If you canceled SLS right now, it doesn't leave us anywhere. There's nothing to replace it, and we will miss that opportunity. So, as expensive as it might be, I think that's the path we're on, and I think it's I know the administration's put forward of trying to do the first three. We'll see what happens, but maybe there's also a time for us to check and figure out what are we going to do after that. That's the problem we've had with our space programs is that we especially after the shuttle was retired, there was nothing to replace it. So look how long it took us. We were grounded for 9 years before we were able to send astronauts to space, and we had to buy tickets on the Soyuz. And I don't think we want to let that happen by just canceling a program without having anything in its place. And Starship is impressive. Catching those super heavies, I love it, but they have to figure out why the last two Starships exploded. And it's impressive technology. They're going to make it. I know they will, but it's not ready yet.
Good answer. We're going to switch over to a more technical design question from Douglas Hall. What finally prompted NASA to cross-feed the orbiter nose prop tanks to the aft main tanks? This seemed like a major obvious design ops oversight.
I'm afraid I don't know the answer to that. That's a technical. That's what I don't know. We can take that and I can try to find that out. But it's funny though. Years ago when I was working in aerospace, I went to a classified briefing, and the guy who was doing the briefing had a rule of thumb. He said, if someone asked me a question and I don't know the answer, I say it's classified. So I can't say that here, but I have to try to find that out. That I don't know the answer to.
Douglas, good question to stump him on.
Yes.
Let's end with one last question. Sure. What impact did the shuttle program have on space policy?
I'm hopeful, and I'm not sure it has done this, but I think it was the wrong way to design a spacecraft. Now, going to the moon with Apollo, we never had a blank check. Government never gave NASA a blank check, but they had enough money to do things, and in case they encountered something unexpected. I definitely understand the motivations of bringing down the cost, but I really think they skimped on the design. I don't know whether it would have looked or done anything differently had they had more money. So I think the key is that you really have to, if you're going to invest in these programs, you have to invest and do it right from the start. And you can't, the space station's another example, changing scope, changing aspects to it. Those things cost more money. They don't save us money. And I think you need to have a sustained policy, but that's really hard to do. But if the shuttle taught us anything, that's not the way to run a program.
Yeah.
Cautionary tale.
Yes.
Well, Burt, I think I speak for everyone when I say that this was a fantastic presentation, super engaging, a lot of information that you shared with us in a very digestible and very cool way. So I just want to thank you for that.
I hope everyone enjoyed it. Yes.
Thank you so much. And I think we should come to the end.
Okay.
And I would like to share my screen. And thank you to the speaker for such an amazing presentation. It was nice to have you. And from wherever you're watching, thank you all for attending this presentation and have a great evening, day, and weekend.